Okay, welcome everyone. Tonight's presentation is Data is Electrons, and we'll get to that right after the news. The first news item is a good one, as in Hubble has been deemed operational and will be back to normal operations in the next week or so. Turns out it was a power controller issue, not computer and not memory problem. So they did some multiplexing of the various redundant components. And so Hubble should be operational again, which is good.
Yay.
For those of you that might be familiar with telescope brands, Meade has finally gone into bankruptcy court and been acquired by Orion. So when you buy a Meade product in the future, it'll actually be an Orion product through the Meade subsidiary. Know that Orion is not Centa, and Centa is Celestron, and the US Federal Trade Commission didn't really want Centa Celestron to acquire Meade. So Orion came up and acquired them, which means they had to be really cheap. They had to be really in dire straits in order for Orion to be able to afford to do that.
So are you saying that's a good thing?
Well, rather than Meade going away, yes.
I bought things from Meade and they seem to be good. So
Well, the last few years have been difficult for them because, the market had a decline and they couldn't get products shipped and they couldn't get product parts to support the products they already shipped. So it was not good. So they filed for bankruptcy, and Centa Celestron was going to pick them up, but that would put too many eggs in one basket for the US telescope marketplace. So Orion's picking them up. Okay, I don't know if any of you have been following I don't know how many of you have been following it, but there have been on and off detections of methane on Mars. The Curiosity rover occasionally and repeatedly detects small amounts of methane, parts per million classification. But the orbiting satellites around Mars were having difficulty repeating their detections. And they've now determined a couple of things. First off, the source of the methane is very near Curiosity. It's only a few miles away. So when the methane comes out of the ground, it kind of pools into the recessed area where Curiosity is located. And since the gas spectroscopy detector operates better at night because it's a power balancing issue, they were doing their gas detections at night. And when the gas comes out of the ground, it pools in the area, the gas detector picks it up. But by next morning, when solar radiation hits it, the methane is in such small quantities that it basically comes apart at the seams and is no longer detectable. So they switched off and started doing detection in the daytime and found out, yep, it's not in the daytime. It's really only at night. And it really is detectable from the ground, but from orbit, they have to detect in daytime because that's how they get solar power to run the orbiting craft. So they're leaving it up to Curiosity to say, yes, it's detected methane on Mars. It is from a source that is nearby. And the Planetary Society has put out a lovely picture showing the cycle of sources and sinks of methane. And as you can see, they have a couple of ways that it could be from UV radiation affecting the chemistry of the surface materials of Mars and decomposing it shortly after it creates it. But they've also left in the lower left-hand corner there something that says microbes. So if it comes up out of the ground, then it's likely that it comes from microbes. But if it's from UV radiation affecting the surface materials, then it's likely just geologic chemistry. So keep an eye out for this. Maybe we have to dig below the surface to find where the bacteria really are. So people probably watched the Branson launch of his spacecraft with him aboard and the landing and such. And on Tuesday, July 20th, Blue Origin will launch Jeff Bezos, his brother, an 18-year-old, youngest ever, and Mercury 13 astronaut candidate Wally Funk, oldest ever, aboard one of their New Shepard suborbital craft. And it'll land via parachute in the desert, not far from the launch site. So it's Jeff Bezos' tourism rocket industry.
By the way, if you want to be part of one of those missions, there are places where you can go to have like a draw for you to go on the Virgin the Virgin.
Virgin Galactic.
Yes, so I got 1,400 tickets to be on the draw.
How did you get that high account?
Well, I paid the maximum.
Oh, okay. And I play the lottery.
Yes, that makes sense. I know the probability is very small.
Yeah, but if I don't win the lottery, I probably am not going to die from it. But if you go up in the rocket and the rocket doesn't make it, you're not coming back, and you paid for it. So,
Well,
I don't
Makes
know.
a difference.
like one more dream, I'll be done anyway.
Yeah, I want to know if I can buy flight insurance. If you do go, can I buy the flight insurance just in case? Because spending $25 to get $1 million in insurance is not bad.
My mom was pissed because I told her about that.
Mhm.
And then, Mom, there is another ticket. You can come with me. No, I won't go. So something happened. You will be upset that you didn't go. So you go with me. If you come back, you come back. If not, we had lots of fun.
Yeah, I hear his windows on his aircraft are smaller than the ones on Bezos's rocket. And you're not truly an astronaut because you're not going above 70 miles, you're only going above 50 miles.
Well, I am already an aeronaut, so
Yeah.
no, I don't care. I have an asterisk anyway.
Yeah.
Oh, I already have one, so.
You have wings, but it's wings on a book. So NASA has this wondrous video that they've put out of the Juno spacecraft doing a flyby of Jupiter's largest moon, Ganymede. It doesn't last all that long, and it's just a zoom by. Juno doesn't go into orbit around Ganymede. It just does a very long elliptical flyby. But it's interesting to see. You get to see Ganymede closer than any other photography's ever seen it.
What is cool is that this camera, the Juno Cam, wasn't supposed to be in the spacecraft, but someone had an idea to have a public related camera where people who could get and take the data and make the pictures. So this video wasn't made by NASA. This was video from someone who just get the pictures and put together and made a video. So this camera is super awesome because we're showing and discovering a lot of things, even amateur discover a new moon in Saturn using Juno Cam. So this was supposed to be just a citizen science or citizen curiosity about, the planets and the spacecraft, and became something super awesome because people are making discoveries, people are making, beautiful things just because they are. That data is available in visible links for anyone to go and get the data. So if you get interested, you can get the raw data and you can, change a little bit and make your video, make your presentation. So it's there for you to actually use it.
The Juno Cam on board Juno is actually the core of it is an off-the-shelf 2 megapixel low light security camera. So it was cheap. It's only 2 megapixels. And they made the presumption that, okay, we're really just going to put it on there for show so that we have some pictures, because the rest of Juno is all scientific data, spectroscopy and measurements and such, which doesn't really wow the public. So to hype up Juno, we'll put a camera on board and let everybody play with the data. And they were suspecting that because Juno flies through Jupiter's radiation fields so close to the planet and so often, now the camera would probably be fried by now. But the camera's done rather well. It's survived all this time and still works.
How close did it come?
It flew within the radiation belts of Jupiter, and it did an elliptical orbit over the pole of Jupiter, which put it in even deeper. So you know, it definitely flew closer than any manned spacecraft would want to fly. It would cook human beings if they were on board. We're into more Comet Hype. There's a comet out there that was discovered in 2014, C/2014 UN271, also known as Bertinelli-Bernstein. It's 62 miles across, 100 kilometers, and it's out beyond Saturn at the moment. So it's not going to come anywhere near Earth anytime soon, but they say that when it gets to its closest approach, it ought to be naked eye visible, but nowhere near that because it's right now at magnitude 19. So don't count on seeing it anytime soon, even visual binoculars or reasonable amateur telescope, but it'll be around in a few more years. And we were discussing the water level in Hoover Dam, and I went looking for pictures of it, and this is a current picture of Hoover Dam and its water levels. And much like in geologic formations, you can see the lines on the sides of rocks as to where water used to be and then where water is now. This is the lowest that the reservoir has been since the 1930s when the dam was built. It is currently at 36% of capacity. It is 148 feet lower than its normal water level. The concerns they have are that it's not only providing water to, I think, 5 states out in that part of the US, it's also providing hydroelectric power to a number of major cities in the area, including Las Vegas. 2 years ago, the few states, I think it's Arizona, Nevada, California, and I think one other state, decided they're going to start cutting back on the amount of water that they send out to these other states from the reservoir, and they did that. But apparently, because of the recent high temperatures, the drought conditions, the water level is evaporating, plus the consumption is still higher than they originally planned, which is why it's the water level is dropping so quickly. And you have to have a certain height of water in order for the hydroelectric power generation to operate at peak performance. So this is something serious to pay attention to. So I've been warning some of my pilot friends about this. United Airlines is buying 100, or has signed a contract to buy 100 electric regional commuter aircraft. These carry 19 people plus pilot, co-pilot. So they're the typical what you would find a regional jet. It has 1 row down each side, and not 2 rows or 4 rows across. And it's only meant to go from hub city to next over city kind of thing. But they're going with electric. They cited the fuel cost, obviously, but also noise reduction, because the electric propellers apparently make a lot less noise and have a lot less noise into the fuselage than does jet engines, and also the maintenance reduction, because the engines are apparently modular and easy to swap out.
Yeah, but they need a very long extension cord.
No, they need a lot of batteries. But remember, these are just regional jets. We're not regional jets, regional prop jobs. They don't fly across the US. They only fly maybe a couple of 100 miles. So look for this as, if they really pull it off, then look for this to be a trend if United is successful doing this.
That could be a problem. They get put in a holding pattern and their batteries start to run down.
Well, always the FAA will say you have to have fuel reserves. So I'm guessing that you'd have to have battery reserves as well. And in the other part of the world of electric things, people are always talking about the potential fire risks of Tesla vehicles. The National Highway Transportation Safety Administration, NHTSA, your government tax dollars at work, actually has put out a recall notice because GM Chevrolet, they put out a recall notice for Bolt vehicles 2017 to 2019. They recalled them, they brought them in for service, they did the repair action. And even after the repair action, 2 of them caught fire. They're now saying that if you want to recharge your Bolt, then do so outside of your garage. So outside, and once you've charged it up for a certain period of time, do not park it near your house or near any other buildings, because the batteries heat up and these seats catch fire, and then that sets the car on fire. So you have a runaway thermal condition on board the GM Bolt batteries that I've never seen that kind of runaway thermal condition on a Tesla, because they do such a good job of battery management. And I posted last week's session on the YouTube page on commercial US spaceports. So that's out there in case people missed it from last week. I did change the description of the YouTube page a little bit. There's a lot more text there. Oh, that's for the video of the YouTube page itself. So if you go to about, if people are curious about it, it explains why are these sessions like, 1 to 2 hours long? Well, it's because the actual live sessions are around 3+ hours long, and then I edit them down, and they're 30 to 45 minutes of news and comments, then the main presentation for 1 to 2 hours. So if you're looking for a 15-minute short video, this is not the place to be looking. And if you're looking for news that has only like 1 or 2 bullet items, no. And as I mentioned the last time, Jill Tarter, formerly of SETI, she's now emeritus of SETI, former chair of SETI. She'll be doing a presentation on behalf of the Astronomical Society of the Pacific Summer Session. Some of their presentations, you do have to be a member. This one is open to the public. So you can go to this page. I'll post the link, and you can go to this page and actually sign up, register for it. So I haven't heard word back yet from the county parks, Broward County Parks, or their STEAM team, their STEAM unit, regarding public outreach for astronomy by Broward Astronomy. The library, the AARLCC library, knows of us. They want us to be there, but they do have to work that through county regulatory. Don't know if they want a special use permit for it being in parks and such, and libraries. Don't know about background checks, but certainly willing to submit whatever is necessary for that. If they want us to have, $2 million worth of liability insurance just for myself or 1 or 2 other people to be there, I would have to talk to them about that. But yeah, if I can get cheap liability insurance through, one of the large astronomy groups like was it Astro League? Yes, Astro League, I think, resells insurance to astronomy groups. So I'll take a look at that. So on July 27th, they'll record my interview with the Broward County Creation Station. They do monthly videos. The format of the video is they interview a person towards the end of their career. I'm that candidate. And they interview a person towards the beginning of their career, which they mentioned was a new NASA employee, but not sure. And that's what they do. They kind of get the opinion of, when you're starting out, how do you think this is all going to work out? Why are you doing it? What do you plan on doing? And then when you get to the end of it, same sorts of questions. How did this work out for you? Would you have done anything different? Is there anything that you would like to have done that you didn't? So that'll be the actual interview. And once they get it recorded, they edit it down, and then they'll post it to the Broward County Videos webpage, which is not as well indexed as a YouTube site. But once they post it, I'll let people know what the link is so you can go take a look at it. And another item of good news, NASA's Goddard Space Flight Center, GSFC, has approved a public event the Saturday after the launch of the James Webb Space Telescope, also known as JWST or just Webb, for me to host a public online session. The currently planned launch is October 31st, so happy Halloween. The actual launch may take place either then or into early November. They're having issues at the launch site. They're going to provide me with access to a NASA subject matter expert to review my presentation content and to be there for the live event to be recorded. So as is typical with Broward Astronomy presentations, expected to be a deep dive into the James Webb Space Telescope. And I found lots of stuff that their frequently asked questions and overview presentations just didn't cover. Things that I had to come out later and find out about the Hubble Space Telescope, like what exactly is the focal ratio of the Hubble Space Telescope? In other words, what are its specifications as a telescope? Diameter, people always talk about the size of the primary mirror and such, but okay, we know this is going to be comprised of 18 hexagonal segments. What is the shape of those segments? Can they move them to accommodate distortions, all those sorts of things? How do they communicate back? What kinds of antennas and radio bands are they used to talk on? Exactly where is it positioned? When can it observe? When can it not observe? So I've got details on all of that I've already drafted into the presentation. Plus, as Helen suggested, there'll be 3D printable model files and paper model files. So for people with 3D printers, there'll be a place where you can go and tinker with.
Has anybody manufactured a plastic model or kit?
Yes, you can 3D print a plastic model. NASA's not making the actual plastic model. They've made the 3D files for people with 3D printers to print the couple of components that get glued together to make the actual model. The paper stuff, I think you have to actually buy different kinds of interesting paper patterns in order to get the right surface reflections and stuff for the material. But different audiences. If you're into 3D printing, there's the files. If you're into making paper models, or you just want to print it on your color printer and then slice it up and glue it together.
Buy the Revell kits and just glue them together.
I
haven't seen a Revell kit for the James Webb yet.
So that is a way for you to actually do printing 3D models. So what you do, you print on a flat page, but that page has a model of a 3D object that you make boxes and you put them together. So I have a Curiosity box, and I did two kinds of Hubbles a few times. That they are at Fox Observatory. So you can actually do a 3D model printing in paper and gluing together. It depends what kind of material you want and how complicated you do it. So if it's just a simple Hubble or James Webb, you use simple boxes, and that is just the drawing. Or there is more details that you can put the layers of the solar protection and the shield, and do the mirrors in shiny paper or even Mylar to make the mirrors. So that is a way for you to do the same model, simpler or complicated. And then there are lots of people who do those kinds of models, like you printing paper in 1D or 2D, and then you close the boxes with glue and you put together to make 3D.
Yeah, there are actually multiple NASA 3D paper models. There's simple ones for younger kids, and then there's very complex ones with lots of intricate detail that you have to go buy special kinds of surface and reflective paper in order to make them. Or you can do what Helen did and do things like, well, for the mirrors, we're going to use aluminum foil. So she has a primary mirror onboard Hubble that's covered in.
I have Hubble here because I need to fix a few things. So I kind of I'm redoing the thing and fixing, but if you can see a little bit, it's shiny. So I printed out in paper that is kind of silvery. And then some of the little details, I use nail polish that's silver. And I have lots of things are removable. So this you can actually open and glue like this as when it's open, so it's Velcro. And then if you open inside, you can actually remove the assembly from inside the telescope. And it's like you can see it's silvery. Let's see if I can do this. So you can actually see that, it's mirrored. And then inside the secondary is also mirrored, and all the little details of
Well,
how it is.
for the web, you're going to need gold foil. It's an infrared scope, so the mirrors are all coated with a thin layer of gold.
So there are little details that I have to fix in here because this was, 2 years be eaten by roaches. Some of the roaches ate one of those legs. And
They
then,
like glue.
little details.
They like the glue, and the paper comes along as fiber in their diet.
Yeah, so I have to fix a few things in this so it can come back to Fox.
Welcome. Tonight's presentation is Data Is Electrons. As some people know, I also work in medical device technology and sensors and transducers and things like that. And when I look below the surface, I find that all these different kinds of measurements that are being digitally made all amount to basically one thing, and that is, counting collections of electrons, typically in something called volts. So I said, well, let me explain this and see what people think. So we measure lots of things. We measure essentially everything around us in order to evaluate things numerically. We do it for comparison. How much is this versus that? Or we do it for communication. We're trying to say, here's the specification in case you want to know, something versus something else you might have thought of that I'm working on. So there's all sorts of ways to do this. There's basically two different classes of measurements. There's analog and digital. And we're going to sort of compartmentalize the analog and set that aside because that's not what we're talking about. Analog is, rulers and tape measures and measuring cups and balance beam weights where you compare two different weights, or pressure gauges that are a spring lever. As pressure pushes against it, it makes the little needle turn. And we'll even put in that analog category something called a galvanometer that is used for swinging a needle to measure voltage. These are all analog. They don't really do anything as integer evaluation of a numerical quantity. But over in the digital category, you have multimeters, you have weight scales, you have cameras, you have astronomy special purpose cameras. All of these are digital measurement instruments. So I've already mentioned the analog stuff. One more analog is counting things. When you have a clicker that counts head count at an event, that is an analog counting device, even though it registers digitally, because you're pushing a button to do it. You're not actually electronically counting it and communicating that out on a display. It's just, rotating gears. And I mentioned the galvanometer. People that have seen this are familiar with it. So long as a voltage is applied, it will energize the coil and the little needle will swing to whatever the voltage reference is. And they adjust the trim on it so that when you don't have a voltage present, it swings to zero. Because if you just leave it on its own, it might not be actually at zero. There's another analog measuring device that I didn't mention, which is weight scales. Spring-loaded weight scales, not the modern high-tech digital ones, but the old style ones where you stepped on it and you heard the recoil of the spring, and then you would see the little dial flipping back and forth. And then when you got off of it, it would kind of oscillate until it stabilized. So that's an analog measuring device, even though it shows a number. So digital measuring devices they're all based upon a small number of formulas that come out of something called Ohm's Law. Georg Ohm in 1827 established the mathematical relationships which result in what some electrical engineers will refer to as the pie chart or the PIE chart. It's talking about power in watts, electromotive force in volts, current in amperes. I don't know why they use I, but amperes, and then resistance in ohms. And that's why resistance is referred to as ohms, because it's named after Georg Ohm. So you'll see that watts equals volts times amps, volts equals watts divided by amps, or you can also say it's volts equals amps times the resistance, the ohms. So very simple things. There are other ways of calculating these that appear in the larger PIE chart, but those involve squares and square roots, and that just complicates things. So these basic formulas work well. They can be evaluated from a passive circuit. So if you have an electronic circuit that you know the components of, and you apply a reference voltage to it, and then you compare that with something that you connect to it to measure, you can say, well, it used to be this value, and now because I've connected this, the resistance has changed, or the voltage has changed, or the current has changed, and therefore that's the number that you display. So that's a passive circuit comparison. When you go to measure things like capacitance or inductance, you need an active circuit. So what they'll typically do is have a frequency generator that will create a little low voltage sine wave, and then you'll connect up your capacitor to it, and it will charge up the capacitor and then discharge it. And it will say, how long did it take to do that? And that will tell you the capacitance of that capacitor. In the case of inductance, same sort of thing. You have a sine wave going through the inductor. Did the sine wave grow or shrink, sort of like a transformer, based upon the inductance of whatever coil you're hooking up to it? So on the inside, it's all about, measuring the volts and then comparing that based upon amps and watts. So you don't actually measure amps, you don't actually measure watts, you're always measuring volts and using the formula to get you back, and then displaying it as watts or amps or volts or ohms. So as I said, you'll take these formulas, fit them into calculations that are done with either electronic components or with a computer, and you'll come up with a number. And the way they come up with the actual number that's being displayed is a device called an analog to digital converter. This is very basic piece of technology that is used in just about everything that produces a digital numeric value out, and it's because it's measuring a voltage. The way it does this is it has a bunch of resistors inside the analog to digital converter. And if the amount of voltage or electrons flowing through the circuit makes its way up through this resistor ladder, it'll flow out over the highest point it can get to, and that turns on a transistor, which puts out an output of, okay, if it gets to this level, then that means it's a 4. If it gets higher, it's a 5. So that's how an analog digital converter works. And here's a little picture of it. You can think of it as if you had a cylinder that had openings out the side of it, and that was the ladders of resistance. As you filled the cylinder, the liquid would come out at the bottom, and as you filled it higher and higher, it would come out at higher and higher levels. And the way it works electronically is it looks for the highest switched output on the transistors. That's why it doesn't tell you all the lower level numbers. It only tells you the highest number, and they encode that as the digital value out of the analog to digital converter. But how good are these converters? If you were to look at them, there's 3 different things that will tell you how good that converter is. It's precision, it's quantization, and it's accuracy. The precision is just, well, how many bits of data are coming out of this? In other words, how many leads are coming out of the analog to digital converter to tell you what the number is. If it's 8 leads, then the most you can have is 255 individual numeric values. If it's 16, you can have 65,000 of them. So it's very high accuracy. The stair steps, these resistor rungs, are integer, they're integral values. So if it gets to 4, but it's really more than 4, but not quite 5, you're still only going to get a 4. So there's no half steps. If you have more bits, now you can come in with additional values in between. But if you've only got 8 bits, you're just going to get a range of 0 to 255. And if you were looking for finer resolution on that, you need more bits. The actual output coming out of it is based upon the bias of the converter. So you could be working in billions of a volt, or millions of a volt, or thousands of a volt, or you can be working upscale with a power meter onto a high power line and working in thousands of volts. The scaling is really on the outside. The analog to digital converter works at very low voltage. And these are not 100% accurate. The resistor that is used to measure the output has a certain percentage of accuracy. If it's not 100%, then you could have what is known as leakage, and you may actually say it's a 4, but it's coming out as a 5 because you don't have a really high quality analog to digital converter. So what is volts? Volts is a count of electrons. Electrons are subatomic particles. These are associated with atoms, and electrons can be exchanged between atoms. An elementary charge is the electrical charge carried by a single proton. An electron is the negative of that charge. There are international standards that have identified what is this charge. The charge is based upon a unit of measure known as the coulomb. And an electron is 1.6 times 10 to the minus 19 coulombs. That's 1 electron. But when you measure a volt, it's a lot of electrons. So you break it down and say, well, how do we step it up from coulombs to volts? And you get other units of measure that they've arrived at, like the joule and the newton and the meter. So what you're actually saying is a newton is the force resulting from a 1 kilogram mass accelerating at 1 meter per second per second. Okay, you may not be into the metric units, but you can think of it as a volt is 1 amp dissipated through 1 watt. So you can relate volts, amps, and watts. It's just an arbitrary packaging of a volt is this package of electrical charge that we measure things on. And rather than measuring things in coulombs, where you would get very, very large, negative numbers to count up all the individual electrons, we use volts as a higher packaging of that. So we don't have to get such amazingly tiny quantity numbers. In chemistry, it's different, because in chemistry, you want to measure moles of a particular substance, and that does get to be very high count numbers. So in chemistry, you'll see a lot of chemistry where you measure the quantities of mix of things by how many moles there are. So sensor data is all about measuring electrons. Whenever you measure anything digitally, you're always coming away with an arbitrary package of volts of electrons. So if you're thinking about any transducer, any way that it measures something, it's typically going to either be measuring the electrons directly, or it's as a voltage, or it's going to be taking what it measures and putting it through some kind of transducer that then converts it to a voltage. So if you're measuring, for example, light, you expose a material to the photons of the light, that produces electrons, it produces a voltage, and then you measure the voltage. And voltage can be positive or negative. So don't think of it as you need a different kind of analog to digital converter. You just run it through an extra bit that says, was that a positive swing or a negative swing? And if you want to measure frequency, frequency is no more complex than a change in amplitude of a voltage over time. So if you measure it really fast, you're just measuring where the amplitude was at those samples. Okay, and then people will say, but what about this kind of measurement or that kind of measurement? What about temperature? Temperature is nothing more than a voltage measurement based upon either direct flow, a thermocouple, you heat it, it produces electricity, or a differential flow, a bolometer or a bolometer. You expose it to heat, to infrared, and it changes the resistance. So that's how you measure temperature. What about heat? Heat's just another way of saying temperature. Light, I already mentioned that if you have photons striking a material that produces electrons, this is known as the photoelectric effect. All you're doing is you're charging up something based upon light exposure, and after a specific period of time, you're discharging it to measure the voltage. Other forms of light, they're all electromagnetic spectrum, radio, infrared, ultraviolet, X-ray, gamma ray, see also light. What about when you measure pressure, when you measure the weight of something electronically? What you're actually doing is putting pressure on crystals that then produce a voltage. That's called the piezoelectric effect. Or you've got a magnet that's moving through a coil producing a voltage. And in either case, you just measure the voltage. When you want to measure sound, you're measuring pressure waves. To measure pressure, you either use a electret microphone or a coil microphone, dynamic microphone. Same sort of thing. You're measuring the pressure based upon the air moving from the sound that it's picking up. Photodetectors, pen diodes and such, see light. What if you're taking pictures or images or doing video? This is nothing more than a whole bunch of pixels, each of them measuring light. Well, what about in astronomy, the difference between CMOS cameras and CCD cameras? This is just a different way of measuring the amount of electricity coming out of the exposure from the photons. What about generating electricity from light? Photovoltaic cells. This is photoelectric effect. This is just producing electricity from exposure to photons. What about gravity waves? This is a new measurement. We must be doing that differently. No, we're measuring a different interference pattern and the changes in the lightness and darkness of that pattern. So to measure gravity waves, we're essentially measuring differences in light, which is producing differences in voltage. So all of these measurements are the same. They're all measuring voltage. They're all measuring how many electrons are flowing past a circuit connection. But you've no doubt seen other digital kinds of things like LED bar meters. An LED bar meter, if you think of that resistor ladder network that's inside of an analog to digital converter, all an LED bar meter is the same sort of thing. As the voltage comes up, it turns on certain LEDs. As the voltage drops down, it turns off those LEDs and leaves others illuminated. When you look at a bar meter in software, when it produces little, bar meter moving back and forth, that's just the same thing as an LED bar meter. It's just done in software, turning on specific pixels or changing the color of them. In radio, you'll often see something called a signal to noise percentage. What is your signal to noise ratio? And all that is two measurements, signal and noise, and then you mathematically compare the two as a ratio. But it's still two measurements, each of which is based upon voltage, the voltage of your signal and the voltage of your noise. Well, what about different scales of measurements? Because you can measure things from mega to kilo to micro to nano and even tinier nowadays. All of those are just scalings off of the concept of an analog to digital converter. If you have a very, very low voltage, you might want to amplify it first, which is just putting in a bias voltage that raises the signal amplification before you put it into your analog to digital converter. If you're measuring negative things, that's just, like I said, it's just a bias on your ADC. It all comes down to measuring voltage, which is just counting electrons. But what about if you're counting and detecting subatomic particles? This is really simple. when you look at one of those pictures of subatomic sprays coming out of particle collision systems, all that is imaging, and imaging is nothing more than different frequencies of light striking materials that produce a voltage, and you're measuring the voltage. If you apply a lot of amplification, you can measure smaller and smaller voltages. If you want to detect different higher and higher frequencies, you sample more often to get the voltages, to get the frequency out of it. It all comes down to you're just measuring voltage, which is just counting electrons. So in conclusion, after you've sort of waded through this, you'll maybe never take a look at digital sensors the same way again, because it all comes down to just measuring volts, which is measuring quantities of collections of electrons. So think about other things in your daily life, and when you see a digital numeric value representing what that measurement is, how is that not just measuring electrons? If you said something like, well, I've got this laser distance measure that I use for measuring the distance from here to a wall. That's just sending out a laser beam and then timing the value back. It just has a tick that says, how long did it take? Well, how does it know when the ticks are occurring? It knows when the ticks are occurring based upon a detector that senses the voltage of when the tick occurs. And then it counts those against a timing source, which has its own ticks. So it just compares the two, but the way it detects the ticks is through measuring electrons. So this was a short one tonight. It wasn't heavy in math all that much. There was a couple of multiplies and divides, but I just found it, people always talk about digital measurements as being different based upon the kind of device they're using to measure it. And when you scrape below the surface, they're all measuring the same thing. It just comes out with different display values.
Monroe, can you explain how a photomultiplier works?
Sure. A photomultiplier tube is something that they use for measuring particle scatters and for measuring star brightnesses. And a photomultiplier.
Radioactivity too? Geiger-Muller tubes.
Yeah, that works the same way. All you're doing is you're taking a specific wavelength of the electromagnetic spectrum and sending those photons to a plate that is coated with a certain material that makes it produce photons. And the photons cascade through additional plates. So the voltage amps up with every switch of the photon to electron conversion, produces more and more electrons. So that's how it multiplies up.
Use them in night vision scopes?
Yeah, they work the same way. All they're doing is they're taking in light and converting that to electrons, and the electrons are being used to amplify that signal to produce different color displays, either through discharge tubes or through pixels in a display. So if you can see, what you have is energy comes in, it strikes a material, it goes through and hits an electrode, that then produces light that then goes through multiple secondary amplifications, and the number of cascades you have dictates how much amplification you get until it finally goes out an anode. So you connect it between ground and an anode and you get a voltage out. And then you run the voltage through an analog to digital converter, and that's how you have a photomultiplier tube. So it's still just electrons, but it does make cascading use of the photoelectric effect. The individual amplifier plates are referred to as dinodes.
Oh, photoelectric effect was one of the Nobel Prizes for Albert Einstein.
Yes.
He figured out that In that case, photons are not a wave, but actually particles. That's when we learned the duality of photons.
Mhm.
And then when you have some wavelength of light that is energetic enough, you can throw a photon in a metal, and that photon emits electron. So
Yeah.
it's like you are actually kicking out with that light electrons.
Mhm.
So that's how the photoelectric effect made us figure out that when you measure the carrier wave of a photon in that form, you make it to become a particle. So you are actually inputting enough energy to a field and you're producing a particle.
Yeah, so you have the photons striking something that produces light, which then hits a material that produces electrons, which cascades to secondary diodes that then cascade through, multiple layers. It's not uncommon to have an 8-layer photomultiplier tube, and just keeps ramping up the voltage until when it finally comes out, it's high enough that you can measure it. This is how you can measure something that may be, trillionths of a volt. Well, a trillionth of a volt is still a lot of electrons.
So the other one that I have difficult to understand is the bolometer.
Oh, a bolometer is simply resistors. So if you take a resistor and you expose it to infrared light or heat, it changes the resistance. And there you go. So you have a resistor that you have a known resistance value, and then you expose it to infrared or heat, and then that changes the resistance. And by the change and the material, understanding the chemistry and the physics of the material, you know that that means this much energy has been applied to it.
Oh, okay. So in that case, some of the bolometers that I worked are made of gallium. Gallium, you can easily change the temperature.
Yep.
And then you make it liquid. So in that case, if you heat like gallium with infrared light, it becomes more, the motion of the crystals of the metal move faster and changing to liquid. And that changes the resistance of the liquid. So now the electrons flow faster and faster. It's like multiply it, how fast those electrons move. Is that?
It's that's the original bolometer. I think it's called a Langley bolometer. But a resistor is a fairly large component. Even if you're making them really small, it's physically large compared to, let's say, a CMOS pixel. So they found new chemistries to make CMOS pixels, and therefore you can now make bolometers that are much higher resolution than heat vision cameras. Because if you've ever looked at a heat vision camera, a genuine bolometer, it's not that many pixels. It's maybe a couple of hundred pixels by a couple of hundred pixels at best. But when you look at a CMOS camera, it could be, a 20 megapixel camera. So why is it that infrared cameras are so low resolution? Because they're bolometers. And there are CMOS infrared cameras, but the materials are so exotic, and the materials are such expensive rare earth materials that you only want to use them in very special instruments, like the James Webb Space Telescope. So the JWST, or the Webb as they like to call it, does have some infrared imagers that are not bolometers. They're actually solid state sensors, but they have very toxic, expensive sensors to get their pixels. And even those are only 2K by 2K. But in order to get the total resolution up, they stage them and have multiple of them. One of the cameras on board the Webb is called NearCam, near infrared camera. You know, science doesn't like to make complicated acronyms. They just like the acronyms, but they don't like to make them complicated. So NearCam is the near infrared camera. But if you look at the details of it, let's see if they have the details here other than pictures of people working on it. Here we go, the technical page. There we go. Technical info. Here we go. So here is the, let's see if it'll show. No, it's not going to show that. Here is the actual imagers. They used, I quote, mirrors to produce two images simultaneously, and they spread them across two different arrays. So they have 2040 by 2040 imaging arrays that are infrared sensors. And they have 1, 2, 3, 4, and then they have another one that's 1, 2, 3, 4, and they can take two different scales of pictures. They can either use all four of them separately, or they can group all four of them together as one image, but then it takes two images, which makes calculating, you know, exposure duration quite difficult on board the Webb. It's not like it is with a normal astronomy camera where you just, I'm going to take a 30-second exposure. No, it's each chip. How much is each chip gathering over a period of time until it saturates? So there's all sorts of calculations you have to go through. But also notice this, if you take a full image with the NearCam, you're going to have this giant gap down the center of it where you have no pixels. And even if you were to take this, you're going to have a gap down the center as a cross on both of them. And you can actually fit stars and small galaxies in these gaps. So it'll be much like the Kepler spacecraft that had a large array of imaging chips with gaps between them. And I'm sorry, if you just happen to be the star that fell in the gap, you didn't get measured. So what they do is they move the imagers. So they'll take snapshot, move, snapshot, move, snapshot, move. That's how they'll get a larger area and cover it all. And the Webb is actually smart enough to do the stacking and integration processing on board the spacecraft rather than sending down a bunch of the individual frames and then having to post-process that on Earth. They actually start the post-processing on board the Webb. Let's see if they have the chemistry here. The sensors in the camera are mercury, cadmium, telluride. That's the chemistry of the actual things that pick up the infrared light and convert it to a voltage. So mercury, yeah, probably something you don't want here on Earth. Cadmium, oh yeah, they have that, you don't want to put cadmium in your products. And I think telluride is not a very common element. So it's expensive and toxic. So it's good to put that out in space. So that's one of the sensors on board. But we'll get into that in more detail. This is kind of a precursor to the level of detail that's going to be in the Webb presentation. Okay, any other thoughts on sensors and measuring things?
Can you just explain with a little bit more detail how a CMOS or a CCD works? Because I've seen presentations showing like the well needs to be full, and that's the measurement that becomes voltage that you can read. Can you like explain that a little bit?
Sure, from some other site.
Charge coupled device, so it's two kinds of metal that's gonna move differently, like a thermostat.
No, if you think back to the days when we had CDs and DVDs and Blu-rays, they're all the same technology. They just use different wavelengths. Well, CMOS versus CCD, they're both just taking light in and producing a voltage out. It's a matter of what are they using to produce the voltage out. In the case of CMOS, it's a very simple per pixel circuit. Here. See, CCD and CMOS imagers both are dependent upon the photoelectric effect to create an electrical signal from light. So they're both taking in photons, having it strike a material, and then the material produces electrons, a voltage. It's a matter of how do you charge that up, and then how do you release it in order to make the voltage measurement. In the case of a CMOS, it's literally you're charging up the material itself. In the case of CCD, you've actually got a transistor switch behind it. So CCD is a little more complicated. So you're not going to get as many pixels in a CCD camera as you do in a CMOS camera. And CMOS just being you're charging up a material and then draining it, it's going to be simpler technology. You can pack it in tighter. But as you make the pixels smaller and smaller, the amount of charge that an individual pixel can hold, in other words, the depth of the electron well, you'll often see this when you look at imaging chips, you'll find an E value. This is the amount of electrons that a pixel well will hold. And you'll find that CCDs can hold a whole lot more because they're not storing it in the material, they're storing it as a capacitance that they then drain with a transistor. Whereas CMOS is actually storing it in the material itself and then draining it out. So they're both using the same technology, bringing in photons and producing a voltage. It's how they produce the voltage and how they drain it out for measuring it. When you drain it out, they're both using analog to digital converters. They're producing a voltage, you charge up all the pixels, and then you work the array of pixels and you release the voltage, and the voltage gets directed into one or more analog to digital converters that then measures, okay, that pixel has a range of 0 to 255 because that's the analog to digital converter's output. If you have a 12-bit 12-bit camera, then that's just because the analog to digital converter is 12 bits instead of 8 bits. The pixels aren't any different, but what you want to do is balance out. If you want to have a lot of variation in your brightness and darkness, what you'll do is you want more electrons in the well. You want deeper wells. And then it's, well, how many bits do you want to draw that out? So if you're counting the voltage, how many divisions do you want in the voltage? Do you want 8 bits? Do you want 0 to 255? You want 12 bits, which is 4096? You know, how many different levels of brightness do you want? Here's the other thing to know about cameras. There's no such thing as a color camera. There just isn't. A color camera is nothing more than a black and white camera with a bunch of color filters put on top of certain pixels called a Bayer matrix, and they have different patterns of red, green, and blue pixels, but pixels are individually just measuring brightness. So all the pixels in a camera do is measure brightness, but they might have a filter on top of some of the pixels to say, well, this is the amount of brightness after going through a red filter. And there's a filter that's so small it fits on top of a pixel. So if you bring in light that is mostly red through the red filter, the voltage, the brightness will be higher because it's not blocking out the green and the blue. So you can judge about how much red or how much green or how much blue, and then you integrate that as a formula across the entire array of pixels that are in this Bayer matrix, and you wind up with a color picture, a color picture, but it's false color. It's representative color.
So it's a mapping, like
Yes.
painting through colors, like
Yes.
in colors through numbers or something like that.
Yes. Think of it this way. If you're serious in astrophotography, you don't buy a color one-shot camera. What you do is you buy a 12-bit grayscale monochrome camera, and then you put a filter wheel on top of it, and you have red, green, blue, and clear, filters. So you can take all the pixels and measure all the red on all the pixels through the red filter. So that gives you not a red picture, but a brightness, another grayscale picture that's all of your red components. And then you do the same thing with green, blue, and then the clear one is just for overall brightness. This is the luminance, the luminosity of your image. And then you use software to merge all that together and you get a higher fidelity color picture because now every pixel can give you a full representation of its color and brightness.
So most of those cameras that we see for astrophotography are CCDs, and most of the phones are CMOS.
That's changing. The number of manufacturers of CCD cameras is in rapid decline because CMOS cameras are so much cheaper to make. And the number of pixels that CMOS cameras have is so large, so many tens of megapixels. And they're making CMOS cameras that are deeper wells, but by having the well be smaller, it doesn't need to be as deep. You can only make it vertically so big when you make it so small. So there's a balance, and astrophotography is moving from CCD-based cameras to CMOS-based cameras, but it's not the garden variety sort of low-grade CMOS that you would see in your mobile phone. It's the higher quality, more expensive, deeper well CMOS that is for low light gathering.
But the scientific instruments still on CCD, right?
No, they're also transitioning. It's just CMOS is just so much cheaper, and they're making higher resolution, higher sensitivity CMOS. So the trend is moving away from CCD to CMOS. Where CCD has a niche is in certain scientific instruments where you want very, very, very low voltage measurements, and CMOS just can't compete with the capacitance wells of CCD. So low light cameras are getting lower and lower. If you think about the camera that's in your mobile phone nowadays, it's likely a 20 megapixel sensor, but it can see in almost total darkness. But CMOS as a chemistry is very sensitive to red light. CCDs are more sensitive to blue light. So as you want to take pictures in infrared, you're going to start seeing more exotic chemistry like the sensors on the web that only see in infrared. So it's kind of funny that the web has multiple spectroscopes. And if you think of a spectroscope, it's, you take a broad wavelength set of light, and then you run it through a prism, and it gets spread into all the different colors of the rainbow. And then at the bottom and the top, you have infrared and ultraviolet that you can't see but are there. But since web is infrared only, it'll do deep infrared and medium infrared. It can't see colors. So all those extra colors that you would see in the visual spectrum that represent all those chemistries, the web won't be able to see those chemistries because it can't pick up those frequencies of light. Whereas the Hubble works in visual. When its spectrograph comes out, it can't get as deep into the infrared or as deep into the ultraviolet, but it's very good at the mid-range color, the visible, all those different rainbow colors, so it can see a wider variety of chemistries than the web will see. So that's the astrophotography chemistry behind the curtain. So when you go out there and you say, I want to buy a good astronomy camera, and I'm willing to spend $1,000 for it because it's a CCD, it's probably not going to be as high a number of pixels as a modern $300 CMOS camera, and it probably won't be able to move the data out as fast since CMOS pixels don't have as many electrons to read out. They can read out faster, and because they are newer technology, they have faster electronics in them, so they can read out faster. So a cheap astronomy CMOS camera may actually be more usable than a very expensive astronomy CCD camera that you bought 5 years ago.